Hello, this is the second lecture for Chapter 2 in biology. We're covering chemistry of life, and so we took a look last time at atoms and how they behave, how all those subatomic particles influence the atoms. So we left off, we were talking about ionic bonds. We now need to spend some time mentioning covalent bonds. Covalent bonds are primarily the type of bond used by living things. Right, so that brings up this term valence. We said that the valence level of an electron is the outermost layer or shell of electrons. This is really important. That's the layer that influences how reactive any atom is. We look at that outermost valence level. So we said in ionic bonding, we move an electron from one valence level of one atom to another. They get opposite charges and they attract. Without the transfer of the electron, we don't get that force of attraction between positive and negative charges, and we don't get a bond. Covalent bonding is different, and I guess the best way to understand this is to look at that term covalent. Right? So covalent bonding has this word valent, which means valence. You co-valence, that is, you cooperate with your valence levels. So instead of transferring electrons, you end up sharing electrons between the two atoms. The electrons spend time in both of the electron clouds around both of your atoms. So a really common covalently bonded molecule is water. So if we have water, we have one oxygen, and that one oxygen shares, and I'm just going to draw the outermost electrons here, that we're going to pay attention to, is going to share its electrons with some hydrogen, and hydrogen will share its electron with oxygen. In fact, since oxygen has two unpaired electrons, it wants to pair up with two other electrons, right? And then we get sharing. We are sharing. These electrons spend time in both of these energy levels, or in both of these molecules. So that is called a covalent bond. All right. Where we pick up in section 2.2, if you're looking at your notes, is because water is bonded with this type of bond, and because of the nature of oxygen, it gives water some interesting properties. So if we say that a covalent bond is sharing, we're sharing our electrons. One of the things we have to remember is not everybody shares equally. If you share equal, that's great. Like if hydrogen's sharing with hydrogen, they would share equally because they have equal pull. This is something called electronegativity. You don't need to remember that term, but you just need to understand that not every atom has the same pull on electrons. Some pull stronger, right? Oxygen is a pretty greedy atom in that it has a high electronegativity, and when it bonds with something, it doesn't want to share equally much of the time. So what happens is sometimes you have equal bonding and sometimes you have unequal. Q-U-A-L, unequal sharing. So when you have unequal sharing, that results in what is called a polar molecule. This is called a polar covalent bond, like the North Pole or the South Pole or the different poles on a battery. There's some difference there. So what that refers to is if oxygen does not share equally with our hydrogen, that means those electrons, which are orbiting this atom, and this atom, right, spend more time around the oxygen. Now, what do we know about subatomic particles, especially electrons? What are their charge? They're negative. What occurs then is because the electrons, which are negative, spend more time around oxygen, this side of this whole molecule becomes partially charged and gets a slightly negative charge to it. It's not an ion, we didn't transfer electrons. It's just that this molecule as a whole becomes a little more negative. And because we have less electron time around our hydrogens, these become a little more positive. Because you have a polar covalent bond, you end up with a polar molecule. Okay? It has polarity. It has weak positive and negative sides. You need to understand this because this helps you understand why water does everything it does really, really good. Right? So water molecules have polarity that creates these forces, these charges. Remember, a bond is a force of attraction. This now allows this molecule, this polar molecule, to exert weak forces of attraction on other things. Those are called hydrogen bonds. So I can pull on something with my positive charges here, and that would be called a hydrogen bond. Now this is a really weak bond. It's not like sharing electrons. That's a really strong, strong bond right there. It's hard to break apart water. It's not very hard to break a hydrogen bond, right? But it's important for living things, and it's important because water gets to do some really cool stuff because it can pull very weakly on something. When you've got billions and billions of water molecules, all of a sudden you're really good at pulling stuff apart, which is why water can dissolve stuff really good. Which that brings us to a couple properties. I'm going to leave that up for now. If you are attracted to more of yourself, where if we had more water, we would then expect that this oxygen would be attracted to these positive hydrogens, because negative and positive attract. So water wants to attract water. Okay, that is what is called cohesion. Okay, attracted to your same material. Okay, it also, this allows water to stick to things, and that's adhesion. It is attracted to other materials. So, here's an example of that. Okay, I have some model water molecules, and you can see on this water molecule, the white represents hydrogen, red represents oxygen. I've got two of them, all right? Whenever I put them together, they stick, okay? Now these have magnets in it, and this is magnets, and it's a good example of water, because water does the same thing on a molecular level. It's not a strong bond, I can pull it apart,
Lacey Lucas,
but they do stick together.
Ah,
another one.
Lacey Lucas, please
And they
come
can
to
just
the office.
keep on sticking together, right? This is due to those hydrogen bonds that are created because this is a polar molecule. Okay, this is cohesion, all right? It wants to stick to itself. This gives you the property of surface tension, how water wants to stick to itself, right? Like it beads up. The little water strider can go across the top of the water and doesn't fall in. It's all because of this, and that's cool. It also allows it to want to attract or stick to other things. That's what makes water make things wet, is when water sticks to it. So I'm gonna get my board wet, and so let's see if it will stick. Will it adhere? Oh look, now I've got water on my board. So that has adhered or used those charges to stick to my board. All right, so that is why water is really good at making things wet. It's good at dissolving things, because what if I drop something in a bunch of water, it's going to pull on it and it will dissolve it. Okay, that's why water's so good at dissolving things like salt water, sugar in water, and it stays dissolved because those weak charges hold onto those molecules of that sugar that you mixed in to make your Kool-Aid. It's holding onto those with those weak charges. That's why water is really, really good at dissolving things. Okay, that's really important. That means, that means you can make a solution with water, and that solution will then dissolve, be something dissolved, which we need to talk about. Okay, in a solution, something's dissolved in water with these charges. It stays very well mixed. Okay, so in a solution, a solution is something dissolved into something else. Okay, the stuff being dissolved is called the solute. And then the solvent does the dissolving. Okay, most of the time, the solvent is water. Water is called the universal solvent because it's so good at dissolving most things. There's some things it can't dissolve, like fats. They don't dissolve in water. But because of those weak positive, negative charges due to its polarity, water is your most prevalent solvent. It's really good at dissolving stuff. Whatever gets dissolved is your solute. So if you're making Kool-Aid, you use up your sugar and your Kool-Aid packet and your water, stir it up, that water grabs a hold of those and dissolves them and holds them all throughout the water, and it stays in solution, right? This is really important for living things because most living things have a lot of water. Humans are like 2/3 of our body by weight is water. So we've got a lot of dissolving happening in our bloodstream and in our cells, and so that's really important for living things. If we couldn't dissolve stuff for living things, then we couldn't move things around inside of us. So that's a pretty important property, right? When we're talking about water, we also need to talk about acids and bases. So we measure acids and bases with the pH scale. pH actually stands for power of hydrogen. So when you say acid or base, you're really, from a chemistry standpoint, you're talking about the concentration of certain ions. We said ions are charged particles, right? So we all know that on the pH scale, it's just a random scale, 7 represents neutral. You're neither acidic nor basic. As you go down from 7 towards 1, this is a range that is considered to be acids. As you go from 7 up to 14, this is considered to be basic. Okay? Now, as you go through this, what really is it that makes something be an acid? There has to be something that makes it an acid. Okay? And this is where water somewhat comes in, and I'll show you in just a sec. Okay? What we're really looking at here is a measure of the concentration of hydrogen ions, or H pluses, right? So the more acidic I am, the more hydrogen ions I have in my solution, right? Now these are reactive because it's a hydrogen ion. It's positive charge, so it's a hydrogen atom that's lost an electron. So that means it wants some electrons and it wants to react. That's why really strong acids, like toilet bowl cleaner or battery acid, is really, really reactive with stuff, is because chemically it has all these atoms that want to react. On the other hand, as you go towards, up towards 14, your basic or alkaline is another term, like an alkaline battery uses a base. You rely on a different ion, the OH negative or hydroxide ion, right? This is also reactive, and that's why really strong bases react with stuff. Okay? Strong cleaners like oven cleaner are super duper reactive. That's why it's good at cleaning stuff, right? So more hydrogens, increasing concentration of hydrogens, you get more and more reactive. Increasing concentration of hydroxide, you get more and more reactive. But what happens if they meet? I think you see what's happening here. When you have H and OH meet, H plus plus OH minus, you get water, or H2O. That's why pure water right here is neutral, number 7. It's neither acidic nor basic. It's neutral, right? So that's where water comes into this, is that if water splits apart, it can make hydrogen or hydroxide ions. But if they're equal, then they're just going to react and just have pure neutral water, right? So living things want to maintain certain pHs. Like you can't live in super acid conditions. Your bloodstream is just slightly basic, but yet in your stomach you have super strong hydrochloric acid to digest the food you eat. So living things utilize these different pHs. Okay, so remember, I guess the big thing here is what makes an acid is more and more hydrogen ions. What makes a base is more hydroxide or OH negative ions. And if they meet, then they kind of balance each other out. Okay, we'll pick back up next time with carbon compounds.